124 light years from where you're sitting right now, a planet orbits a cold red dwarf star. And the most powerful telescope humanity has ever built detected something in its atmosphere that, on Earth, is produced almost entirely by one thing: living organisms. Cambridge saw it, NASA reviewed it, and then, quietly, the scientific world went to war over what it actually means. As of this year, that war still isn't over, and the honest answer is genuinely more complicated and in some ways more interesting than any single headline has captured. For as long as our species has existed, we've looked up at the night sky and asked one question no philosopher or scientist has ever been able to answer: are we alone? For most of human history, that question was pure imagination. There was no instrument on Earth capable of even attempting a real answer. Then, on Christmas Day 2021, humanity launched a machine that changed the terms of that question entirely. The James Webb Space Telescope, a roughly $10 billion mirror of gold-coated beryllium, parked about 1.5 million kilometers from Earth, sensitive enough to detect infrared signatures that no previous instrument could resolve. Here's what most casual coverage misses about what makes Webb genuinely dangerous to old assumptions. Its most consequential capability was never taking beautiful pictures of distant galaxies. It's reading the atmospheres of alien worlds. When a distant planet passes in front of its star, a tiny fraction of that starlight filters directly through the planet's atmosphere before reaching us, and hidden inside that filtered light is a genuine chemical fingerprint. Every molecule, water, methane, carbon dioxide, absorbs light at its own specific wavelength, like a barcode written into physics itself. Webb was built to read those barcodes from over 100 light years away. For the first time in human history, we built a machine that could analyze the air of another world without ever leaving our own. In 2023, that machine turned toward a planet called K2-18b, and what it found there kicked off one of the most closely watched scientific controversies of the decade. K2-18b sits 124 light years away, in the constellation Leo, orbiting a red dwarf star far smaller and cooler than our Sun. It's roughly 8.6 times more massive than Earth and about 2.6 times larger, and it orbits inside its star's habitable zone, the region where surface temperatures could theoretically allow liquid water to exist. But K2-18b isn't a rocky Earth analog. It belongs to a category of planet that doesn't exist anywhere in our own solar system. A sub-Neptune, bigger than any rocky world we know, smaller than any gas giant we know. Researchers proposed a specific theory for what this strange in-between world might actually be: the prototype of a new class of planet, called a Hycean world, a portmanteau of hydrogen and ocean, a planet with a vast global liquid water ocean hidden beneath a thick, hydrogen-rich atmosphere. Hold that image, because everything that follows depends on it. In 2023, a Cambridge-led team headed by astrophysicist Niku Madhusudan pointed Webb's instruments at K2-18b and captured its first detailed atmospheric spectrum. The results were genuinely striking. Methane and carbon dioxide were both detected, while ammonia, a gas you'd normally expect in a standard mini-Neptune atmosphere, was conspicuously absent. That absence mattered because a massive ocean beneath the atmosphere could plausibly dissolve and scrub ammonia out of the sky entirely. The chemistry was pointing, quietly but consistently, toward the possibility of a planet-wide ocean. But buried in that same 2023 dataset was something else, something the researchers themselves treated with real caution: a faint, tentative hint of a molecule. You've probably never encountered that name directly, but you've smelled it. It's a major contributor to the distinctive, briny scent of a sea breeze. And here's the detail that turned a quiet, tentative signal into a genuine scientific event. On Earth, this compound is produced almost entirely by biological activity, primarily by marine phytoplankton, the microscopic organisms drifting through our oceans. There's no major geological process on our own planet that produces DMS in significant quantities. For decades, astrobiologists have listed dimethyl sulfide as one of the more promising potential biosignature gases in existence, precisely because its production pathway on Earth is so overwhelmingly biological. And Webb had just caught a faint whisper of it in the atmosphere of a possible ocean world, light years away. A whisper isn't proof, though, and the research team knew that better than anyone. So they did exactly what responsible scientists are supposed to do. They went back for a second, independent look, using an entirely different instrument, to see if the signal held up under genuinely separate scrutiny. What happened next made headlines around the world, and it's exactly where this story gets genuinely complicated. Before we get into that second observation, and the specific numbers that triggered a real scientific fight over what they actually meant, I want to know. Given that Webb can now genuinely analyze the chemical composition of an atmosphere 124 light years away, does that capability alone feel more significant to you than any single result it's found so far? Drop your answer below and subscribe now, because Section 2 is where this story turns into an actual scientific battle. Here's where this story gets bigger than one single planet. Because while the world was fixated on K2-18b, Webb has been running a much broader campaign across the galaxy, and the results have genuinely reshaped the entire strategy for how astronomers search for life. Some of those results have been sobering. When scientists examined a rocky world called LHS 3844b, a super-Earth about 1.3 times Earth's mass orbiting a red dwarf roughly 48 light-years away, Webb found no detectable atmosphere at all. A bare, airless rock, essentially a larger version of Mercury, according to Universe Today's coverage of the findings. That same disappointing pattern has now played out multiple times across the TRAPPIST-1 system specifically. TRAPPIST-1b, the innermost of that system's 7 Earth-sized worlds. Analysis: no confirmed terrestrial atmosphere has actually been detected there yet, with additional transits still scheduled to further narrow the possibilities. That's a meaningfully different, more cautious picture than a story of triumphant reignition, and being honest about that distinction matters. What genuinely hasn't disappointed is the discovery closest to home, the one we've already covered in detail elsewhere. The strong evidence Webb found for a giant planet candidate orbiting Alpha Centauri A, the nearest Sun-like star to Earth, just over 4 light-years away. If eventually confirmed, following its next observational window in August 2026, it would represent the closest planet candidate ever found sitting inside the habitable zone of a Sun-like star. Was confirmed by a team led by NASA Ames astronomer Thomas Green, publishing in Nature, to have no meaningful atmosphere, ruling out both a Venus-like thick atmosphere and an oxygen-dominated one to a confidence exceeding 6 sigma. TRAPPIST, or 1c, followed a similar trajectory, with follow-up MIRI observations ruling out a thick carbon dioxide atmosphere as well, though thinner atmospheric scenarios couldn't be fully excluded there. A genuine pattern emerged from this wreckage, and it's worth being direct about it rather than glossing past it. The problem increasingly appears to be the stars themselves. M-dwarfs, the single most common type of star in the entire galaxy, force any orbiting planet in their habitable zone to sit dangerously close to the star's surface. Just to stay warm enough for liquid water, close enough that stellar radiation and flaring activity can strip a planet's atmosphere away entirely over time, according to the Planetary Society's own reporting on this exact research trend. Think about the scale of that implication. The most common stars in the Milky Way, the stars that the majority of all planets in the galaxy actually orbit, might be serial atmosphere destroyers by their basic nature. Here's where I need to correct something important and be genuinely honest with you, because this is exactly the point where sensationalized coverage tends to overstate the good news. TRAPPIST-1e, the planet sitting most comfortably inside that system's habitable zone, was widely hoped to be the exception that reignited the entire search. But the actual current observational picture is more cautious than some earlier reporting suggested. According to Universe Today's coverage of Webb's ongoing TRAPPIST-1e observations, after 4 transits, the data currently suggests the planet has likely lost its primordial atmosphere due to stellar flaring activity from its host star, not that a confirmed secondary atmosphere has been detected. A companion research paper on JWST TST DREAMS observations, covering TRAPPIST-1e specifically, notes: the planet is more likely than its innermost siblings to have retained some form of atmosphere, since it receives less intense X-ray and ultraviolet radiation than planets B and C. But, as of the most recent published, to be clear about what that candidate actually is, current evidence points to a gas giant roughly Saturn's mass, not a rocky world, and scientists are direct that it wouldn't support life as we understand it. But it's worth noting, purely as a point of scientific interest rather than confirmed fact, that in our own solar system, gas giants aren't dead ends for astrobiology entirely. Some of their moons, like Europa and Enceladus, are now understood to hide substantial liquid water oceans beneath their ice. Whether anything comparable could exist around a hypothetical moon of this Alpha Centauri candidate is pure speculation at this stage, not an established finding. But it's the kind of question that becomes newly relevant the moment a planet like this gets confirmed sitting in a genuinely habitable zone. Meanwhile, Webb has continued refining our knowledge of other habitable zone candidates with real precision. In the TOI 700 system, roughly 100 light-years away, 2 Earth-sized planets orbit inside the habitable zone, and Webb's observations have improved the accuracy of their orbital measurements substantially, refining planet TOI 700d to roughly 1.145 times Earth's radius, and planet TOI 700e to roughly 0.919 times Earth's radius. One planet slightly larger than Earth, one slightly smaller, both sitting in the zone where liquid water could theoretically exist, and we now know their physical sizes to a level of precision that would have been unthinkable before this telescope existed. So where does that leave the actual central question of this video, the fate of K2-18b specifically? Here's the honest answer, and it's genuinely more interesting than a clean yes or no. The signal hasn't been killed, and it hasn't been confirmed. Hints of dimethyl sulfide persist across multiple independent analyses, but the evidence remains meaningfully below the strength required to claim its definitive presence. Rather than abandoning the search entirely, researchers are emphasizing exactly what needs to happen next. More observation time, more independent transits, more analyses, stress testing the same raw data from different methodological angles. There's a genuine clock running on all of it too, since every transit of K2-18b across its star provides only a brief observation window, open for hours before closing again until the next orbit. Before we close this out in the final section, and look at what's actually coming next to help settle questions like this permanently, tell me, after hearing the real, more cautious picture on TRAPPIST-1e specifically, does that change how skeptical you are of similarly optimistic exoplanet headlines you've seen elsewhere? Drop your answer below and subscribe now, because the final section brings together where this entire search for life is actually headed. Let's bring this entire story together, because what we've walked through, K2-18b's genuinely contested biosignature, the string of airless rocky worlds around red dwarfs, TRAPPIST-1e's more cautious real status, and the still unconfirmed giant planet candidate at Alpha Centauri, adds up to something more honest, and in its own way, more genuinely exciting than any single confirmed discovery would be on its own. We've reached the actual edge of what our most powerful current instrument can reliably see. Webb is, quite literally, brushing against the boundary of detection on some of the most important questions in the field, and coming up just short of full certainty. The K2-18b signal sits right there, flickering between 2.7 and 3 sigma, never quite crossing into confirmed territory, never quite disappearing into pure noise either. And that persistent, unresolved flicker, more than any single confirmed headline could, tells you something genuinely important about exactly where we stand in this search right now. Here's the encouraging part, and it's not speculation, it's already funded and actively under construction. We are one real instrument generation away from being able to answer questions Webb simply wasn't built to fully resolve, and those instruments are already being built. The European Southern Observatory's extremely large telescope, the largest optical and infrared telescope ever constructed on Earth, is scheduled for completion in 2029, with a mirror vast enough to potentially detect the kind of thin, Earth-like atmospheres that remain genuinely beyond Webb's current reach. NASA's Nancy Grace Roman Space Telescope is set to launch by May 2027, potentially as early as fall 2026, carrying hardware specifically designed to hunt for planetary systems exactly like Alpha Centauri's. And behind both of those sits the true long-term endgame, the Habitable Worlds Observatory, currently in early phase planning at NASA, being designed for one explicit, singular purpose: to directly image Earth-like planets sitting in the habitable zones of sun-like stars and analyze their atmospheres specifically for biosignatures. Not to study galaxies, not to map dark matter, to find living worlds. Full stop, as its actual stated mission. There's a genuinely important implication buried inside that mission plan that deserves real attention. Even if the Habitable Worlds Observatory ultimately finds no signs of life anywhere it looks, it could still survey enough planets to place the first genuinely rigorous scientific limit on how often detectable life actually arises on Earth-like worlds across the galaxy. Think through what that actually means for a moment. Either outcome from that eventual survey reshapes our understanding of our place in the universe. If it finds life somewhere, we're not alone, full stop. If it surveys dozens of genuinely Earth-like worlds and finds nothing at all, that itself becomes powerful, sobering evidence that complex, detectable life might be extraordinarily rare. Rare enough that we could plausibly be among the only witnesses this galaxy currently has. There's no boring, inconclusive result waiting at the end of that particular road. Every realistic outcome from that future observatory rewrites something meaningful about the human story. Pull back now and look at the complete, honest picture, because this is exactly what the fragmented, sensationalized headlines about individual discoveries consistently fail to show you together. In the span of roughly 4 years, one single telescope has detected genuine chemistry on a plausible ocean candidate world and caught a real, still disputed whisper of a molecule, Earth's own oceans, exhale through living plankton. It has directly confirmed multiple rocky worlds around red dwarfs are genuinely airless, reshaping our entire understanding of what habitability around the galaxy's most common stars actually requires. It has found strong evidence of a genuinely unexpected giant planet candidate orbiting the nearest sun-like star in existence. It has measured Earth-sized worlds 100 light-years away with a level of precision that would have sounded like science fiction 20 years ago. And it has done every bit of this while operating right at the ragged edge of its own technical capabilities, which means everything we've covered across this entire video represents the floor of what's coming, not the ceiling. This isn't chaos, and it isn't a field in crisis. It's convergence. Every line of evidence, every instrument. Currently under construction, every mission timeline currently funded is genuinely bending toward the same point on the horizon. A moment, perhaps, within the next decade or so, when a spectrum finally arrives from some distant world and the signal doesn't flicker, uncertainly at 3 sigma. It holds cleanly at 5. On that day, whenever it actually arrives, a scientist somewhere will look at a screen and realize they're the first human being in roughly 200,000 years of our species' existence to know, with genuine scientific certainty, whether we're alone or not. Until that day comes, we live inside the open question, and there's something genuinely remarkable in that too. We happen to exist in the narrow sliver of human history where this exact question has finally become answerable, but isn't yet actually answered. Our grandparents could only wonder about it in the abstract. Our grandchildren will very likely simply know, I want to hear where you land on all of this. After walking through the real contested state of the K2-18b signal, the sobering pattern of airless worlds, and the genuine instruments already being built to finally settle these questions, do you think we're closer to a real answer than the headlines usually let on? Or do you think this specific search is still fundamentally further away than most people assume? Drop your prediction in the comments. I read every single one. And if this breakdown gave you the honest, fully sourced version of this story, instead of the oversimplified headline version, do me a favor, hit subscribe, tap the notification bell, and share this with someone who still thinks this question was already answered. Because based on everything we just walked through, it genuinely hasn't been, not yet. Thanks for watching, and I'll see you in the next one.